Good evening, gentle readers. It's October 15th, 2024. From a desk with Ross Finlayson here in Seattle, Washington, is today's Moment in Motion. Geometry is motion. So I wasn't quite sure what would be the theme of today's talk, but basically what it is about dimensional analysis, the mechanics of motion and dimensional analysis, and the dimensioned yet dimensionless, the dimensional analysis, and geometry as motion and projection and perspective. That those are very complementary concepts that make, in many ways and profoundly and yet vacuously, yet in the total, these kinds of combined concerns, the perspective and the projection, that motion and geometry, both together with perspective and projection, are these things from each point of view as it is and as they are. So kind of in these conflations, the confusings, the joinings, the foundings together of these things, that the geometry and motion and perspective and projection make it, that they're almost always set together, yet they float freely apart. That this way, this deconstructive account makes for then this elementarily distinct theory of the elements of geometry and form and proportion and motion and statics and dynamics, which one of those is in front, as with regards to then perspective and projection, as with regards to the projective and the perspective, as have been discussed here many times. So that just goes to say that it's intended to make for that. It's further emplaced that the projection and perspective are these first-class sort of concepts in geometry. As motion. Geometry is motion. And perspective and projection are what occur when things are in motion, as with regards to how they observe each other, which isn't just for the matters of the senses, but the matters of all this state. Because in our universe, according to our mechanical model of physics, every single physical thing affects every other single physical thing, as we all inhabit the same field that is indistinguishable, and there's this attenuation and dissipation bit that reduces, there's a floor, sound of the ocean, maybe, that's how it is. So with regards to perspective and projection, those are the key concepts to introduce, go along with the geometry as motion, that otherwise the geometry as motion is its own very sort of particular kind of wheel, with regards to that of being a centralized sort of continuous forward yet in place action, rotation, and then that rotation is free. Geometry is motion, rotation is free. Perspective and projection, there's only 3 space dimensions, and then that's how it is. So the dimensionless is another thing to try and figure out, because what happens is the dimensionless is very apropos, because particularly and exactly because the dimensional analysis is totally apropos. In our physical setups, we have only exactly what can be observed and measured. That is what is scientific, basically. And the fact that the universe has the same laws everywhere, that there is a theory that holds true, holds good, as Einstein puts it, kind of is unfalsifiable the other way. And also it's kind of pretty much so that it's never been shown, well, sometimes it's kind of shown, but it's never been shown across like the premier theories like relativity and quantum mechanics put together these days, that the laws are any different anywhere. And so when they had that for this dimensional analysis, what happened was 20, 30 years ago was the big test called the Wide Microwave Anisotropic Background Explorer, WMAP. The idea was like WMAP is going to look at the cosmic microwave background radiation of the whole universe, and if it can find anisotropy, not isotropy, if it can find anisotropy, then that would indicate that there's either a gradient or a shape or something as with regards to the background. And if it finds isotropy, then that means the universe is flat, and then it's the same laws pretty much everywhere, right? So what it was arrived at, that was a great, and there's among other things that could be measurable and falsifiable and observable. But when WMAP and then the CMBR came up and said, the universe is flat and it's pretty much isotropic. If there's a gradient, it's nominal. If it's non-zero, it's vanishing, like the cosmological constant. So that being the case, then at least it makes a very, very strong statement that the laws of physics are the same everywhere, and they have been forever. There's no time, place, or other surrounds of any kind of condition where the laws of physics do not apply. Now, that doesn't preclude the super scientific, which can be any number of super classical effects as with regards to the instantaneous behavior of things, however so far separated in terms of space at any given time. Or as with regards to the compounding effects like the echoes of waves, which could last for a long time and persevere until such time as like a rogue wave appears or something like that, or otherwise that an event could be lost in the floor yet still achieve distinctness or something like that. That just saying that doesn't necessarily at all say anything different about the laws of physics, that they're always the same. And then in the statics and in the usual case, it's always most simply the sum of history is sum of potentials bit, with the oscillation restitution, the attenuation and dissipation, the tendencies and propensities, that just being this sum of history, sum of potentials with this gradient, the forward carriage of time, and then that implying thusly this vanishing, non-zero, positive yet vanishing forward progression of time is constant. So the dimensional analysis, thusly, with the meter stick and a stopwatch, or is with regards to a meter stick, a stopwatch, and a right angle, or a compass, tools of geometry, say, and that establishing a metric, or the length of things up close, and a norm, or the length and the distance of things far away, was just establishing the space-time. This way can, even in a world with relativity, where sometimes the idea is like space-time is curved, it's just whatever makes a geodesy, that everything according to gravity just falls straight down, and everything that's going, however it's going around and round or in a straight line, is according to this way, Minkowskian, where it's let out as free, the extra dimension, even if it's time. That in this sense, where it's otherwise kind of disproved, or made it much less tenable for there to be it, so that the space-time was curved in that sense of that any histories never diverge and never could meet again. There's no closed time-like curves, meaning there's no backwards time travel. Everything is always going forward in time travel. It's just that they could go at different rates, in a sense. Space-time is still, in a sense, fundamentally, utterly flat. And then that gravity would have to be is synchronous thing as well as an isotropic thing. It's not asynchronous and it's not anisotropic, according to just the latest, greatest sky survey of the day, since about 30 years, and that's been the case. And also they discovered that some of the microwave background was not just electromagnetic, also infrared. And so that basically said, oh, well, this is discovered. It says, are you picture the universe as it could be Big Bang or steady state? Either way is a good deal. It's just, it came into existence. It's always existed. both unfalsifiable, both fit in the numbers, laws of large numbers. Okay. So the dimensional analysis here and what I wanted to get to today for mechanics is length, distance, because they're the same units, meters. But one is like the length at a particular time, and the velocity is like the displacement of that length per given time. And then there's displacement or distance is traveling that according to the position, the displacement for a given time is from here to here. And then there's related notions of speed and velocity, that speed is like going in the direction that is its current heading in direction. What is that velocity relative to the most at rest background, if nothing ever really is, whatever is at rest in the background. Because here mathematically it's like, yes, there is 0 meters per second and there is 0 seconds per meter, although it's less likely to find 0 seconds per meter when that's infinity meters per second. Yeah, it's, up and on the infinitely many higher orders, it's arbitrarily a non-zero yet vanishing infinitesimal quantity of how long that is equals 1. The hypercube distance equals 1 again, right? That for these kinds of concerns that otherwise we have in the classical all these kinds of gives, saying it's like, well, we can't have a universe that's ever really at rest, and everything's got to be in the ideals that came up in the last couple talks specifically. Like the theory of Einstein's relativity is just given one ideal by taking only one negative statement of a case of relativity as for motion in this absolutes in the ideal. That otherwise we have all of Zeno's arguments to fulfill and all the classical paradoxes of motion, and that otherwise it would be grainy or discrete, and the latest greatest sky survey always has tended to disprove this. And there's no least instant of time. Time is infinitely divisible, compounding then that it's also in that infinite divisibility, it's the smoothness of its grain between the 0 and 1. For that we need mathematics. We got mathematics of continuous domains, line reals, field reals, signal reals. We build standardly our field reals because we're using just the same laws of arithmetic that everybody got taught since first grade. And we're using no theorems that involve infinity at all, except we have the limit and delta epsilonics to give us a fundamental theorem of the derivative. And then as with regards to the fundamental theorem of the integral, we have Riemann sums, and we just kind of make one example for that and then prove everything afterwards from the geometric series. And then later in higher mathematics, we get into weak and strong, uniform and global, fast and slow, convergence. In the cases when they're not in each one of those, and when they're not like fast, strong, global convergence, what is going on with that? That these laws of large numbers. So mathematics has these at least to give it, it's continuous, the background. It's isotropic, it's continuous. The cosmological constant of Einstein's gravitational field equations is non-zero and is vanishingly small. It's an infinitesimal. So then that just kind of gives that's time. It just kind of that's its ramp, and it's just kind of naturally just floating, falling in time this way. So that's very satisfying to a certain extent, because it gives all of the classical expectations of the Newtonian that have an interplay with regards to the theory of general relativity, and separately this theory of special relativity with regards to the the massy and of matter, the charged, and then the nuclear and radionuclear, electron, proton, neutron, photon, 4 different fields usually in unified field theory, the elements in these theories, that it gives some of that back. And then so that helps a lot when it's like our best knowledge of the Earth's ephemeris and how it rotates around the solar system with everything else is this parameterized post-Newtonian model. That's the theory, the practical working theory. It helps a lot when that makes a lot of that stuff back to being just usual simplified calculations. Yet still we have stuff going on when length and length over time and distance are not the same. So that's getting into then the Lorentzians and the Galileans, where the Galilean is the most usual. And you can also ascribe that to just be Euclidean, because it's just, as far as a straight line goes, it is an aliquot, or it is just a rational computation. It is classical. So that's still on. That's where when the units fall out of that, it's like, well, of course it's dimensionless, because they're not explicit, and they need not be, and they it's just meters per second, and then over time as the number of seconds equals meters. This dimensional analysis, the dimensioned. Yet there's also the dimensionless, the dimensioned, and as with regards to when you think of whether it's taken like a taxi cab path where it's like there's only right turns, or it's taking kind of like the path of orbits, where there's a general idea that everything is always moving in orbits, and even when it doesn't enter in like a natural orbit of a larger body or something like that, like a satellite's orbit around the Earth, or the Earth around the Sun, or any satellite around its star or its center, is that the orbits make this orbifold, make the trajectories, make the orbifold, and this trajectifold. So rolling back from the concepts from the descriptive differential dynamics is the orbifold and the trajectifold. So after the continuous manifold is the vector space on that of any single thing, its motion as a vector. And so that's its velocity vector, say. This is an orbifold, it's a trajectifold, it's the vector field, the vector manifold. It's a continuous manifold. There are no experiments falsifying the essentially fundamentally continuous background reality. We all know quantum mechanics. We all know particle wave duality. We all know the Planck length and things to do with like what appear to be discrete orbital, elementarily quantized particles and quantities. Then we also know about beta decay and muons and they're continuous again, and the tremendous success of spectroscopy, and what it is about the angstroms and the Plancks that in the atomic scale of the Democritan and Avogadro's number, that's part of our regime of the measurements of electron physics. It's continuous again, is my point I'm trying to make here, because both that satisfies the mathematical, that there's nothing so grainy that could satisfy, because otherwise there would not be a universe with a geometry with both right angles and straight lines. So there would be no metric anywhere. There would be it results via deduction that the background of the space is a continuous manifold, and then that there exist any singularities in the sense of actually that the space-time is so curved as to fall apart, or that it would, if anything was to affect something like a meeting of those spaces, like the wormhole concept, or otherwise a folding of this manifold space-time, and it folding together and apart, that is still all as together somehow continuous. That goes without saying here. So then the dimensional analysis, what I'm trying to figure out is that when it's both meters per second and distance over time, with regards to those being the same units, there's all this ideas of what it's gone through to get there. And so here, then, those discussions have been about the walk integral. That's kind of what's been going on here, is a walk integral. The Zeno's swath as a complement to, these are basically in reflections upon what's called the path integral. So the path integral is from quantum mechanics. And what it intends to entail is that the line integral is just adding up the pieces of a path, so you could measure the length of a particle's track according to its passage. And in the line integral, you're summing together the line elements, this path. And the path integral is that when it's like, it's a wave, so it takes all the possible paths. Basically, seem like between point A and point B, call it Heisenberg 1 or Heisenberg 0 and Heisenberg 1, or A and B. Then with regards to insofar as it reaches a given point, and as if it reaches another point to form a wave pattern, like a proton or an electron or a stream of these particles, that the only way it could so form and present as wave-like characters this way, that the path integral intends to sum up all those possible paths, when abstractly it's still only linear and geometrical, that it's also optical and wave-like. So it's this extra character that it has. So it's anything different than the path integral than what's otherwise the line integral. So the path integral is kind of a product of the 1950s and 60s, the mathematics of it. And so it's kind of novel. But when it's heard of it tends to become very, very relevant to particle wave duality. Because particle wave duality, when the waves are models of change in an open system, or rays or particles, has that they're not line-like. They're arbitrarily positive, vanishing, yet with an extended. They have an extended body. The waves, the wave packet, the wave front, vis-a-vis just being a point-like particle. So the path integral is one of the profound concepts after particle wave duality. Then there's Heisenberg's uncertainty, position or momentum. Here, for example, where we're talking about the dimensioned yet dimensionless character of position, and the pseudo momentum and its conservation in and out of these kinematic systems. So fundamentally, Heisenberg uncertainty. And then there's the Schrödinger picture. So the usual models of the quantum mechanics involve the Heisenberg picture and the Schrödinger picture. And that these, in terms of the path integral, in terms of time ordering and line elements, that then it makes basically an infinitude of line elements, and it constructs an argument for an infinite limit, a continuum limit. And then with regards to the non-classical part, these contributions as regards to the surrounds, the path integral, and those being about, like if the atom is 25 orders of magnitude smaller than us, that they're about a third of the way out or half the way out, or a quarter of the way out, I guess. It being that the linear line integral would be 1.000000020 more zeros, whereas the path integral looks like 1.000000000, and then like 6 to 10 zeros, and then 1, 8, 1, ... and the rest, and then some more zeros, and that this is like the second spectrum kind of these tiny quantum scale contributions then that add back up to make scattering and tunneling theory what it is, according to the mathematics that then make for quantum mechanics and quantum electrodynamics and quantum field theory, not so much, but quantum chromodynamics and quantum electrodynamics is very, very much employed. The path integral. So the idea of this walk integral is not like adding up the waves components. It's more like as an anthropomorphic bipedal animal with 2 feet walking forward on 2 feet on a path that is a path integral, then that it's just as the any given step, it's always going forward, whether or not it turns or not, so that it's arbitrarily contained, that it's constantly kind of lurching forward, and then that this adds up all the momentum that goes along through the whole thing, that it's in the kind of the frame of the object itself instead of its surrounds or where it's going through its track, say, the track. So it's then there's considerations of these kinds of notions for the round track, like a running track, or a straight track, just a section of track. And then as with regards to these things, and then that the Zeno swath is kind of like the path integral. The path integral is like a wave being added up over a line segment, where the Zeno swath is more like this Manhattan or taxi cab distance, where it's like all the right angle turns. Because something that's linear is like, it lives in a rectilinear world where everything's kind of like a rectangular square. It's a hypercube, and all these possible dimensions it could be, that when that reduces becoming just a path, any given path, that this hypercube distance equals 1, that Zeno swath is the path that is in that hypercube, as that 0, 1, which is this walk integral. And then as with regards that also it's kind of this walk integral at the same time the stop derivative. That the stop derivative and the walk integral are kind of the differintegro and the integrodiffer parts of each other. And then to just fill that out, then the idea is that there's this pause integral and a run derivative, figuring that the running is flat out and that a pause is kind of like an arbitrary moment in the quasi-motion for something that's balanced and stately and gainly, and basically at any given step can instantly pause and make any given step from any moment of pause or not. That when something's running, it's running flat out, and if it trips, it falls over. But something that's walking can pause and stop, vis-a-vis something that's running that's coming to a stop is also kind of linear. So in this way, you can kind of see that these two complementary pairs each make also complementary pairs to each other. The stopping and running and pausing and walking, and running and walking and pausing and stopping. That this way it helps make it so that then in each of these, because it does involve more conditions and cases than our usual, what we're talking about here, the laws of motion. Galileo's and Newton's classical laws of motion. Motion, rest, equal opposite. Force equals mass times acceleration, and gravity. Where here the idea is that what we're getting into is relativity theory, picking up kind of where Einstein also is trying to figure out what's going on with mechanics of motion and the spatial and spatial, and helping get that reorganized a little bit. That being about space contraction in the relativistic dynamics. That applying to the Lorentzians for the Galilean and the Fitzgeraldians and the Maxwellians for the cases in the theory of relativity where motion is relative, and the other ones, for example, where it's absolute and what that means when it is. These ideals, they're all ideal theories and they're all classical in the limit, yet somehow none really classical, because the real fields are the potential fields, and it adds up that the classical limit in the middle is just the trace of the potential, which is so great. That let's see. So then for the mesoscale mechanics of the active force, was the idea to figure out. And then for gravity, there's fall gravity on mostly isotropic, vanishing positive gradient, fall gravity. So it's thorough. This, what would you call it? The force equals mass times acceleration then is with these ideas of the V viva and the V motrix. So the V motrix is what we have today. It is the Galilean part, and it is the Newtonian part. And what it is mass times velocity equals momentum. And force equals mass times acceleration. Great. So what's wrong with that is only what's kind of missing from it. And it's that any change, when you apply the arguments to your mind about how these things would have their causality, that one thing leads to another, that their cause exists, with regards to first principles and the final cause of things, that any force cannot go from 0 to 1 in a 0 time, because that would give it a velocity of infinity. And so that would make it an unstoppable force, and thusly that seems untenable, unreasonable. It ends up being not sensible, fungible, and tractable. Although modeling it as not an unstoppable force, but just over a unit time, an application in reverse, saying that, well, something changed in velocity, so its posterior determined acceleration must have been this. So the force for that time on average was that. But it couldn't have started at all, or it couldn't have ended, except as with an infinite quantity. So the idea is that then there must be infinitely many higher orders of acceleration, of which those go to be non-zero. They're nominally non-zero, yet vanishing. So that the entire sum of those then is then in smaller increments, is never infinity. Yet it is an infinitary expression itself that must exist for there to be any kinds of smooth changes in motion at all. Or, for example, in a world where you might consider as like nothing's really at rest ever at all, if it goes from one displacement to another, or ever has reciprocating motion, it will have cross zero at an instant at least. That then it can't be excluded, and it's similarly like if you try and consider like, well, what if there's just a granularity and it just jagged jumps over this and is always fractal and indeterminate and never a real quantity and never an observable, measurable, fixed quantity or continuous quantity. That's sometimes what people are, led to arrive at, because otherwise they'd have to allow in this entire notion for sure. So otherwise, then maybe they don't. But then as well, you can see how then that leads to that there is not rest in that universe. And the flip side of it is that there's not motion anywhere. It's just jumps. And then all the laws start just in the regress, the reductio, or the double reductio, the reductio, it falls away. So space-time is continuous. Force is a function of time. Acceleration has infinitely many higher orders of acceleration. So that's been talked about pretty thoroughly before, and then that gets into the hypercube distance. It's infinite dimensional, and then that just all falls down immediately to 1.0. Hypercube distance is 1.0. Motion occurs, and all classical laws are just so in the limit. It's great. Then what I want to talk about today mostly was the how you say dimensional analysis after perspective and projection. So let's see if there's some light left here. Here's some books. This is Notes on Complexity, a Scientific Theory. And so what I thought to do with this was just kind of look about some of these things about with complexity is we have convergence and its complementary concept, emergence. So convergence is where a finite quantity results from an infinitary expression and a sum of that. It's not necessarily infinitary. I mean, sometimes there are closed forms which result convergence, or if it's just like it goes to a constant and it's reached its limit and it is there for the convergence and emergence make a thing. So when you hear about complexity and the theories of complexity theory and the emergence of things, that is about convergence and convergence and convergence again. And it's about entropy and entropy again. And so convergence and emergence are complementary theories. The atomic level, ATP, RNA and DNA, actin and myosin, cells and molecules, parts, boundaries, perspective, molecules, the Gaia hypothesis, or Gaia. Is the Earth a living organism? Likely. It's on an entirely different scale of things, and one where, for example, it's the entire epochal of like radiation lifetime would make more meaning than in terms of it. It's like everything in our classical mesoscale is just moving around at light speed and is vanishing and has zero mass, but it could add up. And we only live on this one green Earth, and that's the way it is, fellow Earthlings. Well, I got this. I'm going to look this some more. He's talking about, and then with regards to, he mentions here a chapter on the Vienna Circle and scientific empiricism, and there's been discussed here quite a bit about the cyclic metaphysic and the teleological approach to re-emplacing within scientists' logical positivism, a briefer yet thorough and inarguable metaphysics, as just, if there's a physics at all, the physics, it's mathematical, plainly, and technical, that thusly some of these other questions of the existentialism and nihilism have answers again. Because otherwise, then the philosophy of existentialism and nihilism to satisfy logical positivism are left again with nothing to sustain them except empirical materialism, which are not scientific and lead to usually tragedies of the common vis-a-vis the human condition, which it contains both tragedies and the divine, or that which is the sublime, say, the human in it. So that's part of philosophy, and then consciousness, and then can people think alike? Yeah, people think alike all the time. And this other thing I wanted to look at for a while was this. Maybe I set this aside to read or so, because what I was looking for, it was called The Hard Problems or something like that. Let's see if I can find that. Oh, here it was. No Easy Answers. And so this fellow is Alan Franklin, and he's part of the physicists. And what he had in here that I thought was of interest was earlier in these talks, we were looking at the Stern-Gerlach experiment and how it is so that it establishes that there is continuity. And so that was kind of the result. It's like Feynman set it up. He's like, here, I'm setting it up for you. Here's how it looks. Here's what we can say it is. Here's how it comes around. And what must it be if it comes around? It must be somehow a continuous process. Okay. Yet it's wave-like. And so it kind of stands itself up as a wave-like thing. Yet when people have to also kind of apply to it the particle conceit, then it's an issue. And so what interested me in this was that there was a picture of its perspective or the projection the particle makes in the Stern-Gerlach apparatus. So the Stern-Gerlach apparatus basically has a deflection of a beam of particles, and so it's either positive or negative or zero. And so then you usually think of that as just plainly tri-state. Positive, negative, or zero. And then what came of it, though, when looking at the diagram, it's like it makes a bubble, and then off to the side is also a whisker. And so it kind of sets itself up to be like, well, that's like curving terrestrial, meaning what the idea is that the fields are so weak as with regards to yet that's where the trail is or the track is, that it's aligned with more stuff to do with the ether hypothesis, that the Earth in its track is in a space, and the space and the frame go together. And so then there's also anything that's right outside of it that isn't carried apart as the rigid body that's the object is also a different space. So these spaces pass each other in the trajectifold and the orbifold and the trajectifold. So that's kind of the idea of the ether hypothesis is then, on the Earth, we can't tell the difference according to the equivalence principle from g-forces and gravity of Earth, the acceleration in our gravity well, the Earth's. But right outside of it, you can, and you can also measure it, what that is. Even if you're outside of it, you shouldn't be able to detect it at all because it measures what it's like off outside of that. And then that falls away again too, or kind of grows into what becomes the sun's frame, because the sun is going arbitrarily faster around the center of the galaxy than the Earth is around the sun. And it's also kind of like gets into lots of things going on in the larger scale. So that just goes to say that this Stern-Gerlach experiment that I've been reading about here got into a bunch of things to do with the theories of gravity also going on in this book called No Easy Answers, because there were a bunch of experiments that I hadn't really heard about in the 80s and 90s with regards to stuff like gravitational torsion measures next to a cliff, or where the potential makes it so that instead of like the Newtonian, like two bodies gravitate and they pull each other together, then there's the fall gravity, is this idea that instead of two objects get pushed together, like there's an outside field and everything just kind of shakes itself free or loose, and so the two objects fall together in the middle, that it's kind of like there's this fall gravity or shadow gravity, that the gravitons, the low energy gravitons, are of these various sorts. Because quantum gravity is always kind of coming up as a thing, is like if two objects move together by gravity, somehow there's got to be an exchange of particles among them in the particle theory. So otherwise the particle theory has nothing to say about that. And so you hear about these days, you'll hear about quantum spin foam. That's one of the premier theories of quantum gravity today. And it's kind of it's between the atom, the objects still, as with regards to, that's like the force vector that we observe, that gravity holds them together, or that's what's perceived that they hold together. The quantum spin foam. But then the other, and that's like Kelvin's vortices, Descartes' vortices. Congratulations, back again. Yet another thing that seems necessary in perspective and projective for geometry is motion, for a natural continuum as a spiral space-filling curve, and line drawing, of course, all from axiomless geometry, which arises from axiomless natural deduction. That at least that's the theory of everything. So that's the theory of everything and all that's in it, which is pretty great. So fall gravity at this point in time then is saying, well, this makes sense when the sum of potentials has that it's a potential field is the real field. So the objects aren't working for gravity, that they arrive at each other. Instead, they're just both in orbits together, and then they block out the rest of the universe with regards to each other. They're only passively participating in gravity. So thusly, by these objects passively participating in gravity and not violating the usual law of conservation of energy, that they still, it's like they us as ants on the Earth are terrestrial, and the gravitational and the equivalence principle balance right out. They just do. I mean, that's kind of the definition of then that being the arbitrarily larger body that then returns in terms of real orbifold and trajectifold and microgravity. That's the sum of potentials from the outside is the fall gravity, and then that it just adds up inverse square is inverse square and kind of like that spike the way they connected. But there's as well this more outer well or the cone of it is with regards to the light cone is a familiar concept, like this is the future, the light cone. And then as with regards to the gravity cone is like this is the potential, this is the well of gravity. Otherwise undisturbed, that's the flow of things, the flexibility. So that goes quite a way into like a theory overall of things. And so what I wanted to mention was, as I got started, was the perspective and projection, and then the dimensioned and dimensionless, and then how these space frames and frame spaces have their orbifolds, trajectifold, and what that means with regards to otherwise their course of passage, and this kind of thing. And then with regards to the perspective and projection then is to get back to the ideas of the perspective and projection. Because perspective, it has two aspects of the sensory act of vision itself. The idea of the intromissive is that the images, the films we see of Lucretius, or the images of Fresnel, or the images and the photons, the rays that activate the cones and rods of our eyes, and the pigments within our eyes, and their particular nature and properties with regards to the tristimulus color space of the special character of optical light, which is special. The optical vis-a-vis otherwise the ionizing and the difference between electromagnetic radiation and optical and then radionuclear radiation. As that the intromissive is the usual idea that it's what comes in is what we see. And the complementary concept of that is the extromissive, and the idea that when you look at something, it actually sends out a beam, kind of like if you have the difference between this passive intromissive vision and an active extromissive vision is when the light from a laser or a light beam or a sonar or radar, anything that produces a wave that is expected to deflect off something else according to the passage it makes through and arrive back, that is intromissive and extromissive. The concepts of the active and passive, or respectively. So that is into the perspective and projection, because the idea is that though we don't have extromissive vision, at the same time, the projection is both that perspective and meeting that perspective. So as our eyes aren't fixed, what would we call it, installations, as it were, then as well everything from the gravitational wave observatory to all the other senses get to the fact that all the senses, even beneath their floors, where they're measurable, detectable, and observable, combine. And so then it makes for so which ones are kind of in effect. That as well, this convergent and emergent can arise from that. When as with regards to that, while each is so specialized, and according to the medium, and according to the conditions, and according to the floor, the signal, and that it all results into a theory of information theory called signal theory or information theory. Then we get to the concept that in a Newtonian universe, the speed of information is infinite. And that in the Einsteinian universe, it's set up that the speed of information is limited, fixed according to light speed, which is a constant in the theory. So here in this theory, there's still very much so that it's a natural law that light speed in a deep space in a vacuum is a constant. And so there's the light is always fleeting, flux, and fresh here. And then there is as well, though, that the gravitational has the field of gravity always points the force vector of this gravitic or gravific, whichever it so is, as directly pointing at the source, not the image, which according to the senses is after the passage of the light's film, the image, that Earth's gravity pointing to the sun is pointing to the sun, not its image. And similarly, the Earth's gravity pointing to the moon is pointing to the moon, not its image, which is only that few light seconds behind, or only insofar as it's any different. That's just to be said that according to the best measurements of the ephemeris, that according to the way the solar system is in its static state, in this epoch, in this era of the time, that gravity's instant effects are so instantaneous. So information is free in that sense. It's metered, and then, for example, as by light speed, anything that would intend to entail the massively reduced costs of the propagation of information in image at light speed moves for free at light speed. Whereas anything that could be contrived as an entire gravitational setting across large or cosmological scale distances has that as so afforded by its economy of the things. So in that sense, with this kind of theory, it can be just seen that while it's still both a relativistic theory and an Einstein's relativity, and it's a Newtonian theory too, then that these kind of give us the Galilean and Newtonian laws and this Einstein's relativity theory. Then as well, these few other simple associations, kind of this rest exchange momentum and a bit of light speed rest frame theory, but that being just that SR is local, and then there's much to be figured out for keeping all the invariants up in this world of these running constants, where we have fresh light and running constants, that thusly it can be sort of more of a theory of everything, and all at one time, as it were. Well, that's a little bit later in the evening. It's past the summertime, so this far north, the days and it gets shorter and the nights get longer in terms of the winter. So with that said, then I'll just kind of run out the clock here and try to figure out. There's a few more things I wanted to mention. So it was perspective and projection, and how relevant those are, and how fluid those are with regards to geometry and motion. Yet at the same time, they kind of, I just kind of see it as a pinwheel, which is like, it's like a wheel with vanes, and it's pinned to like the end of a piece of straw, so you hold it in the wind and it spins in the wind. It's a pinwheel. And that's kind of like just the notion of the free rotation of that as with regards to its orientation and its measurement of any kind of gradient. Here, the wind, the measurement of the wind. That is kind of an aspect of a sense of touch that is for example, it's specialized and of the many different kinds of senses that affect to reflect the scientific observation. And the other idea, and it would see a lot more development, is the dimensioned. And so what was framed with this was that distance and length are not the same. And the metric and norm are both totally significant, and they both reflect the same measurement at the time. And then it was with regards to the reemplacement of the dimensions in those when they're dimensioned quantities, yet dimensionless, according to what results as the severe abstraction, the mechanical reduction, as we've read from this, our theory, our canon, the science of and the definition of mechanics according to the United States and the Western canon of 30 or 40 years ago. The severe abstraction and mechanical reduction has that, then it gets into these notions of not much more than the usual first laws of mechanics of motion, but these simplest sorts of zeroth laws that then bring in where there's just one continuity and just one infinitary, and then that kind of suffices for then the differintegro and the integrodiffer, and those are to get figured out a little bit more thoroughly. And then that reflects on things like the vortices and the quantum spin foam, the real graviton as both the atom its own, and then also gravitons, these fleeting of flux, the ultramundane corpuscles, and finally something like the Higgs boson is like the last graviton. I mean, that's up in the free energies or the in the supersymmetry of the unification of the field theories. That's like, well, according to our Tivatron and its highest energy particle colliders at all, yeah, the Higgs boson is kind of like a graviton, but that the graviton it is the atom itself. See, the atom itself is like, if light is a special sort of ray, then the atom is a special sort of particle, and it's with regards to the conserved quantities, invariance more generally, the speed of light, the mass of the nucleus of the molecule. That this is great, then at least then all the theory and all their primary theories still kind of are together and the same. Whereas at the same time, these just briefest superclassical accoutrements result that then it's much more close to being a fulfilled theory of everything with less. Well, gentle readers, that's what there is of this for today. The idea of perspective and projection for geometry is motion. So geometry is motion. And then for the dimensioned, there's just the idea to explode all the possible dimensions that there are when considering this severe abstraction, the mechanical reduction, the perfectly classical and the linear, and mv, motion times mass times velocity, and then mv squared, and what that means, just that's what was meant to get into, was the v viva then is, well, the velocity is twice as active because it represents anything going around too. And you got the inside and outside of the forces and virtual forces whether it's reflected and whether it's relative, one way or the other, because in systems where their bodies are about the same, it's a reflection. Where systems or bodies are not, it's an invariance. So that gets into cases, and it's necessarily so that gets into cases. So there's that, and then there was the notions that back to perspective and projection of the senses, and the idea that information is free if metered, and that ticks all the boxes. Well, so long.